Section: Introduction. In this section, we discuss the advancements in large language models, particularly those based on transformer architectures, which are widely used in natural language processing. However, these models face challenges due to their quadratic self-attention mechanism, which requires extensive computations between all tokens. This limitation has led us to explore alternative subquadratic models, including approximations of self-attention and entirely different architectures like state space models, SSMs. While training robust subquadratic models like SSMs can be beneficial due to lower fine-tuning and inference costs, they have not received as much attention or resources as transformers. This prompts us to ask whether we can utilize the extensive resources invested in training quadratic time transformers to enhance alternative models like SSMs. We propose a method for training subquadratic state space models, specifically Mamba SSMs, by distilling various components from a pre-trained transformer model. Our main idea is to view both attention and SSMs as ways to transform sequences by mixing token embeddings using different matrices. We can break down sequence model architectures into two parts: sequence mixing and channel mixing. For example, a transformer consists of attention for sequence mixing and MLP for channel mixing. This breakdown allows us to distill the mixing components of each model at different levels. We introduce a three-phase distillation process that progressively targets higher levels of guidance from the teacher model. First, we align the sequence transformation matrices. Second, we align the hidden state representations of each layer without losing previously learned information. And third, we conduct end-to-end training with weight transfer to distill the final output using only a small amount of training data. We call our approach MOHAWK, reflecting these three stages. We apply our method to a modified version of the Mamba 2 architecture, named Phi Mamba, which aligns more closely with the architectural blocks of the strong PHI 1.5 transformer model. Our Phi Mamba model outperforms previous Mamba models of similar size on benchmarks, achieving notable accuracy improvements with significantly less training data. For example, it reaches 71.7% accuracy on the Winagrande dataset, compared to 60.9% for the pre-trained Mamba 2 model. Additionally, by retaining only 4 attention layers and replacing the other 20 with Mamba layers, our hybrid model achieves an average performance of 66.0% on selected evaluations, closely matching PHI 1.5 feet's 67.2%. Interestingly, our hybrid Phi Mamba performs comparably to or better than Samba, despite Samba being trained on a larger dataset and having more parameters. Our results demonstrate the effectiveness of our three-phase distillation approach, as each phase significantly contributes to the final model performance. We also highlight the advantages of state space models, especially when trained on fewer tokens than the original pre-trained Mamba model. Section Summary. In this section, we discuss the limitations of transformer models due to their quadratic self-attention and introduce our MOHAWK approach for distilling subquadratic state space models from pre-trained transformers. Our method, which involves a three-phase distillation process, enables the Phi Mamba model to achieve superior performance on benchmarks with significantly less training data compared to previous models. Section: SSM Architectures. In this section, we discuss SSM architectures. GSS was the first to integrate SSMs into gated neural networks for language modeling. H3, which combines S4 and linear attention, uses SSMs with shift and diagonal matrices along with multiplicative operations on input projections. This approach has been expanded to include broader recurrences, laying the groundwork for future architectures. Selective S4 treats S4 as a black box that creates a binary mask for the input, similar to gating mechanisms. Mamba combines the H3 block with the common MLP block by interleaving them, resulting in a more powerful architecture. The Mamba 2 block simplifies this by generating SSM parameters at the start of the block instead of depending on the input. MAMBA2 SSD is a variant that utilizes structured state space duality. The core layer of Mamba 2 is significantly faster than Mamba's selective SSM while still outperforming transformers in language modeling. Next, we explore knowledge distillation, which allows us to transfer knowledge from a larger teacher model to a smaller student model, making it more efficient while maintaining performance. This technique has been applied to various language tasks, including text generation, machine translation, and question answering systems. Most work in this area has focused on compressing larger pre-trained transformers into smaller versions by using the teacher model's weights. Some methods resemble ours, such as matching attention matrices and aligning outputs of each block. However, our approach differs in key ways, particularly in the loss function and the independence of block alignment. Previous studies have found that combining objectives can hinder distillation, while we demonstrate that our methods significantly enhance the student model. A smaller number of studies have aimed at distilling across different architectures, particularly converting a pre-trained transformer into a similarly sized recurrent model. Some initial attempts involved transferring weights to create linear attention, while others matched attention matrices. Our method stands out by using a more constrained loss function, incorporating detailed alignment steps, and utilizing advanced efficient student models like Mamba 2, which we show are easier to distill. To clarify our distillation approach, we provide essential background and definitions, along with an overview of the Mamba 2 architecture, which underpins our Phi-Mamba model. We refer to the function that represents the input and output of a sequence model as a sequence transformation or mixer. This term describes a parameterized map on sequences, where we combine tokens at different time steps to help the model understand temporal information. Sequence transformations are fundamental to deep sequence models and are key components of neural network frameworks like transformers. A specific type of sequence transformation can be represented by a matrix, known as a sequence transformation matrix or matrix mixer. For instance, vanilla self-attention uses a softmax matrix applied to input-dependent data. We can also derive causal variance by using a lower triangular matrix. A straightforward way to compute the output of a sequence transformation is to multiply the input sequence by the matrix. However, this method has a time complexity that becomes impractical for long sequences. To tackle this issue, we have developed subquadratic sequence transformations like Mamba 2, which improve efficiency through structured matrix multiplication. Section Summary. In this section, we explore various architectures that integrate structured state space models, SSMs, into neural networks for language modeling, highlighting innovations like the Mamba 2 block, which enhances efficiency and performance compared to traditional transformers. We also discuss knowledge distillation techniques that improve model efficiency by transferring knowledge from larger models to smaller ones, emphasizing our unique approach that incorporates fine-grained alignment and a constrained loss function. Section MAMBA 2. In this section, we introduce Mamba 2, a new type of structured state space model, SSM. Like the original Mamba model, MAMBA 2 employs a time-varying state space model that can selectively focus on or disregard inputs based on its input-dependent parameters. This time-varying SSM is characterized by specific projections of the system, with one component being a scalar multiplied by the identity matrix. Unlike its predecessor, MAMBA 2 treats the underlying sequence as coming from a discrete signal, eliminating the sampling aspect found in the original model. We establish a new link between SSMs and transformers, which we call structured state space duality, SSD. This connection shows that a specific type of SSM can be interpreted as a form of causal linear attention. By fixing certain parameters, we can derive causal linear attention, where specific matrices represent the projections of the key and query, while another matrix corresponds to the value projection. Inspired by this relationship, we demonstrate that the SSD mixer family in MAMBA 2 is equivalent to a type of matrix known as sequentially semi-separable matrices. We note that the Mamba 2 architecture can be seen as causal linear attention with a learnable causal mask. To improve the Mamba 2 matrix mixer, we designed the Mamba 2 block, which modifies the previous Mamba 1 block. We introduce parallel parameter projections to reduce the number of parameters and enhance tensor parallelism, along with an additional normalization layer to stabilize training in larger models. Although we have made some changes, the Mamba 2 block remains similar to its predecessor. For a visual representation, we refer to the architecture figure, noting that we have removed the normalization layer before the final output projection and discarded the nonlinear activation after the convolution operation. Next, we outline the phases of our method, MOHAWK, which includes matrix orientation, hidden state alignment, and knowledge distillation. These phases are essential for creating an effective student model from a pre-trained transformer model. Unlike traditional distillation methods, our student model retains the overall structure of the teacher model, differing only in the attention matrix mixer, which we replace with a subquadratic alternative. We will gradually reveal our architecture, Phi Mamba, and detail its distillation process. This section concludes with a thorough description of the Phi Mamba architecture and its hybrid version, which outperforms other subquadratic matrix mixers. We also discuss the effectiveness of our method and conduct ablation studies. For clarity, we define a block as the repeating components that make up the end-to-end model. These blocks consist of layers, including the self-attention layer, the SSM layer, and the convolutional layer. Many transformer models, such as Llama, are structured as stacks of alternating self-attention and MLP blocks, while our Phi and Phi Mamba models consist of Phi blocks that include parallel attention, SSM and MLP blocks. In the first stage of MOHAWK, we focus on aligning the student matrix mixer with the teacher's self-attention matrix. This alignment involves two steps. First, we ensure that the components before the matrix mixer in the student model match those in the teacher model. This guarantees that the input transformation is consistent up to the mixing process, with the only difference being the matrix calculation. We then minimize the distance between the matrix mixers of the student and teacher models. In our experiments, we use the output from the teacher model's previous layer as the input to better align the distributions. This stage can be executed in parallel across all student layers since the inputs to both student and teacher blocks are the same. For Mamba 2, we start by setting the convolution to an identity function, which minimizes its initial effect. This allows the semi-separable matrix to be the main difference between the layers. We then work to minimize the distance between the two matrix mixers, the semi-separable scalar identity and the attention matrix. Our findings highlight the significance of this stage in the distillation process, showing that the Mamba 2 matrix mixer is more expressive than many alternatives and can effectively approximate the self-attention matrix across various data samples in a transformer model through gradient descent, establishing it as a robust sequence mixer. Section Summary. In this section, we introduce Mamba 2, a structured state-space model that enhances the original Mamba by incorporating a time-varying state-space framework and establishing a connection to transformers through structured state-space duality. We also outline the MOHAWK distillation process, which aligns a student model's matrix mixer with a teacher model's self-attention matrix, ensuring effective knowledge transfer while maintaining the overall architecture. Section Stage 2, Hidden State Alignment. In this section, we focus on Stage 2, which is about aligning the hidden states. After optimizing the first stage, we need to address the differences between the outputs of the student and teacher blocks. Our aim is to align these components by minimizing the difference in their outputs, specifically between the Mamba block and the self-attention block. We can perform this alignment in parallel across all student layers. For Mamba 2, we adjust the remaining components to match those of the PHI 1.5 attention block to maintain functionality from Stage 1. We start by setting the gate to a constant value of 1 to keep it open and remove normalization before the output projection since it cannot align with the attention block. We then work to minimize the distance between the outputs of the Mamba 2 block and the teacher's self-attention block. Our analysis shows that this distance is closely linked to the model's ability to learn from the teacher, and better alignment leads to improved performance, emphasizing the significance of this stage in the distillation process. Moving to Stage 3, we aim to fine-tune the student model to match the teacher's performance. Even though we have aligned the student and teacher mixing blocks, there are still differences between consecutive blocks in the network. To address this, we transfer the remaining weights from the teacher model to the corresponding components in the student model. For Phi Mamba, this includes the token embedding, final layer normalization, language model head, and MLP and input normalization at each block. We then fine-tune the entire student model under the teacher's guidance, using a distillation loss to help the student mimic the teacher's output distribution. We believe that much of the information in language models is stored in MLP blocks, so we adjust the student blocks to use the MLP similarly to the teacher model, effectively swapping the teacher's matrix mixer with that of the student. Interestingly, we can keep the MLP weights frozen while maintaining performance, showcasing MAMBA2's expressiveness, which is crucial for replacing attention. This approach reduces the number of trained parameters significantly and helps prevent the student model from forgetting the teacher's information. We validate MAMBA2's effectiveness in this regard. Finally, we introduce the Phi Mamba architecture, which combines the Mamba 2 model with the PHI 1.5 transformer model. It consists of a stack of Phi Mamba blocks, initialized and distilled as previously described. We also present the hybrid Phi Mamba variant, which retains 4 layers of attention from PHI 1.5, leveraging the strengths of both models. The Phi Mamba architecture differs from the standard Mamba 2 by modifying the SSM matrix mixer, removing certain components, and incorporating dense layers from the teacher model. Specifically, we modified each Mamba 2 block by removing post-convolution activation and pre-output projection normalization, while setting the gate and convolution to identity functions. Although these components were beneficial for performance when training Mamba 2 from scratch, we find them unnecessary for our distillation process. We made 2 key changes to the Mamba 2 matrix mixer, converting the SSM head structure to a multi-head format, similar to the multi-head attention in transformers, and treating the sequence mixer as entirely discrete time by making the matrix a projection of the input and eliminating the discretization parameter. While this formulation differs slightly from Mamba 2, the original algorithm can still be applied as a black box method. Section Summary. In this section, we outline the final stages of our distillation process, where we align the outputs of student and teacher models and transfer weights to enhance the student's performance. We introduce the Phi Mamba architecture, which integrates the Mamba 2 model with the PHI 1.5 transformer, optimizing the structure for effective knowledge transfer while reducing the number of trained parameters. Section: Empirical Validation. In this section, we begin by looking at the downstream evaluation scores of our MOHAWK distilled Phi Mamba 1.5b and hybrid Phi Mamba 1.5b models. We demonstrate that they outperform all previous subquadratic and hybrid models while also being more efficient in terms of time and memory usage. We then analyze our 3-stage framework in reverse order, breaking down how MOHAWK affects the transfer of learned representations to the student model. To create a baseline that reflects the ideal Phi Mamba distillation process, we used MOHAWK to distill a PHI 1.5 model into another PHI 1.5, transferring all weights except for the attention layers, which we initialized from scratch. We provide details about our final Phi Mamba model in the training section. Next, we outline the architecture for the hybrid Phi Mamba and discuss the adjustments made regarding the number and placement of interleaved attentions, as well as a limitation that may arise from the distillation process. We also explore MAMBA2's ability to learn interactions similar to self-attention. We examine how well a Mamba 2 sequence transformation can mimic a self-attention matrix and whether this ability is present in a comprehensive language model like PHI 1.5. We validate that our MOHAWK framework achieves superior performance on various downstream benchmarks compared to previous subquadratic models of similar size. We distilled the PHI 1.5 1.3b model into Phi Mamba 1.5b and hybrid Phi Mamba 1.5b. Our final Phi Mamba model was distilled using 3 billion tokens from the C4 dataset, with a sequence length of 2048. This is less than 1% of the resources used by many leading subquadratic open-source models. The hybrid Phi Mamba 1.5b was distilled using a budget of 5 billion tokens from the same dataset. We present a detailed breakdown of downstream evaluation results for our models and various baselines on standard common sense reasoning and language understanding tasks. We also show the performance of Phi Mamba and hybrid Phi Mamba against training costs compared to other open-source models of similar sizes. For the experiments in this section, we used the Atom W optimizer with specific parameters and a warm-up stable decay scheduler. In Stage 3, we focus on weight transfer and knowledge distillation, which involves a straightforward end-to-end distillation of teacher model outputs. This stage fine-tunes all components of the network together. Our experiments highlight the importance of this end-to-end alignment, as all three architectures achieved their best scores after this phase. The significance of this alignment varies by architecture, with models that have more mixing layers similar to the teacher model showing less reliance on this phase. Stage 3 is the only stage that trains the student model end-to-end and is considered the main stage. While many distillation methods only use this stage, our findings indicate that relying solely on end-to-end knowledge distillation is not optimal. Although using only Stage 3 is slightly better than only Stage 2 for both Phi Mamba and hybrid Phi Mamba, there is a notable difference when comparing Stage 2 alone to the combination of Stages 2 and 3. We also found that this phase can freeze all network components except the Mamba 2 sequence mixer without significantly affecting performance, suggesting that Stage 3 can function in settings with limited computational resources. However, we observed occasional spikes in loss during this phase, which can negatively impact the model. We addressed these spikes through checkpointing, weight decay, and gradient clipping, leading to a more stable Stage 3. Section Summary. In this section, we empirically validate that our MOHAWK framework outperforms previous subquadratic models in downstream tasks while using significantly fewer resources. We detail the distillation process of the PHI 1.5-1.3b model into Phi Mamba 1.5b and hybrid Phi Mamba 1.5b, highlighting the importance of our three-stage approach, particularly the end-to-end alignment in Stage 3, which enhances performance across architectures. Section Stage 2 Hidden State Alignment. In this section, we evaluate the second stage of our process, which focuses on aligning the hidden state outputs of mixer blocks. After analyzing the model's end-to-end distillation in the third stage, we assess how this alignment affects both the third stage and the overall performance of the model. We train Phi Mamba instances from scratch using various token counts in Stage 2, and then we move on to Stage 3 training. This allows us to see how the extent of Stage 2 pre-training influences Stage 3 performance across different token budgets. Our findings, illustrated in the training laws for Stages 2 and 3, show that models starting with lower hidden state distances after Stage 2 perform better than those relying solely on knowledge distillation in Stage 3. These lower hidden states also correspond to lower initial perplexities, which relate to better downstream performance. Additionally, our ablation studies reveal that combining Stage 2 and Stage 3 yields better results than using knowledge distillation alone. We find that when only Stage 2 is applied, the closer the student model is to the teacher model, particularly in shared attention layers, the more significant the performance impact. However, when we combine both stages, student models that differ more from the teacher model show greater performance improvements. For instance, Phi Mamba, which has no attention layers, improves more than its hybrid counterpart with 4 layers. Next, we explore the first stage, which involves matching matrix mixers to further reduce the hidden state distance from the teacher model. We again assess the impact of this stage on subsequent metrics and overall performance. Our results indicate that even a brief Stage 1 training period can enhance the performance of Stage 2 models, leading to better hidden state distances compared to those trained from scratch. This is despite the divergence and reconvergence of the teacher and student mixers in Stage 2. We also confirm that lower hidden state initializations lead to improved perplexity and downstream performance, suggesting that Stage 1 supports the overall distillation process. Finally, after validating the importance of all 3 stages, we distill the final Phi Mamba model using the MOHAWK framework. We allocate 80 million tokens for stage 1, as this amount shows strong performance in both matrix and hidden state distances. For stage 2, we use 160 million tokens, as this amount appears to saturate hidden state distance and perplexity effectively. We apply stage 3 across a total of 3 billion tokens but encounter training instabilities due to the previously optimal learning rate. By reducing the learning rate for stage 3, we alleviate these issues. We believe the instability arises from the similarity between the Mamba component of the stage 1 and 2 initialization and the teacher model, which, when combined with a high learning rate and disconnections between blocks, leads to training challenges. The performance of our final model is detailed in our downstream evaluation results. Section Summary. In this section, we evaluate the effects of hidden state alignment in stage 2 on the performance of subsequent training stages and overall model effectiveness, finding that models with better hidden state alignment outperform those relying solely on knowledge distillation. We also demonstrate that even minimal training in stage 1 enhances the hidden state distances and overall performance, confirming the importance of integrating all 3 stages in the distillation process for optimal results. Section: Hybrid Phi Mamba Model. In this section, we discuss the hybrid Phi Mamba model. Recently, we have seen models that combine attention mechanisms with SSM layers, such as Samba and Mamba Vision, which perform better than using either method alone. We found that adding a few attention layers increases training and inference time significantly, but this is less of an issue due to the limited number of layers we used. We created a hybrid version of the PHI 1.5 model by keeping 4 original attention layers and changing the rest to Mamba 2 blocks using MOHAWK. This hybrid model achieved a downstream evaluation score of 67, which is close to the pure attention transformer's performance and surpasses the Phi Mamba average score of 68. The hybrid Phi Mamba model also competes well against other attention Mamba hybrids in the 1.5B size range while using fewer attention layers and parameters. We present results showing the effectiveness of different placements for the 4 attention layers in hybrid models. All placements yielded strong results, but our experiments suggest that evenly interleaving Mamba 2 layers leads to the best performance on downstream evaluation benchmarks. This finding aligns with Samba's solutions, which also indicate that interleaving attention layers within Mamba layers enhances performance. We also explore how varying the number of interleaved attention layers affects outcomes. Based on previous findings, we conducted these experiments without converting the attention layers in the network while using MOHAWK for other layers. As expected, maintaining more attention layers improved results. However, we believe there is still potential for enhancing hybrid model distillation due to possible differences in the distillation process between hybrid and non-hybrid architectures. Factors like additional gradient updates and changes in optimizer settings could be optimized further, which we plan to address in future work. Next, we examine how well Mamba 2 can learn interactions similar to those taught by self-attention. We first assess how a Mamba 2 sequence transformation can approximate a self-attention matrix. Then, we investigate whether this capability is present in an end-to-end language model like PHI 1.5. We begin by testing various matrix mixer families to see how well they can replicate the self-attention matrices from a pre-trained transformer. We sampled 1,000 instances from each layer of a Llama 2 to 7B chat model, created the attention matrices, and projected them onto specific classes of structured matrices. The results, averaged across all layers, show that for linear attention matrices, the rank is limited by certain projections of the input. For multi-head linear attention, the head dimension is typically small, as seen in PHI 1.5 and Llama 2 to 7B chat. We approximate this family using causal low-rank matrices, where a lower triangular causal mask is applied, and the head dimension is much smaller than the sequence length. For the multi-head Mamba 2 matrix family, we use the state space dual layer similarly to linear attention, but with a more complex causal matrix structure. Both causal low-rank and SSD matrix families were approximated using gradient descent. To approximate the general class of SSM matrix mixers, we employed balanced truncation, a projection method not reliant on gradients, which is known for model reduction in time-invariant systems and adapted for time-varying systems. For causal matrices representing convolution operations, we used a heuristic to minimize error for each attention matrix. Our findings indicate that while the SSM matrix family closely approximates the self-attention matrix mixer, the Mamba-2 mixer family is only twice as far from the SSM matrices, compared to linear attention, which is 3 times as far, all while maintaining a similar computational cost to linear attention. More details can be found in the appendix. Section Summary. In this section, we present the hybrid Phi-Mamba model, which combines a limited number of attention layers with Mamba-2 blocks, achieving competitive performance while using fewer parameters. We also explore the ability of Mamba-2 to approximate self-attention matrices, finding that it closely matches the performance of structured matrix mixers, particularly the SSM family, while maintaining computational efficiency. Section: Self-attention replacement in language models. In this section, we validate the capability of a Mamba-2 block to replace an attention layer in a language model. We first create 2 versions of our architecture, Phi-Toplets and Phi-LR, and apply the MOHAWK process to 1 billion tokens at each stage to ensure our previous findings hold in a multi-layer model. Next, we conduct MOHAWK while freezing different parts of the Phi-Mamba modules. This shows that when we limit the trainable components to just the Mamba-2 blocks, excluding the embedding, head, and all MLP layers, we only see a slight drop in performance during MOHAWK distillation. Notably, we observe a consistent link between the projection distances of the matrix, measured by the Frobenius distance, and the performance metrics, like accuracy, across various tasks. Essentially, a better matrix approximation, indicated by a lower Frobenius distance, correlates with improved model performance, reflected in higher accuracy. This relationship underscores how the quality of the matrix approximation impacts model effectiveness. Our findings align with previous research, which indicates that more expressive matrix mixers lead to better performing models, such as low-rank-based BERT models outperforming those based on toplet structures.